Let me talk about that, and then I'll talk about the one question that people had the most trouble with on this test, and then we'll go on to new stuff. So exam 3 is Monday the 29th. And the topics for that, we're not going to do any free body diagrams on that. So it's everything up through 2D kinematics of particles. And it's cumulative, so be sure that, you look back at the old stuff too. Anybody have any questions about the test? Okay. Exam 2. The biggest problem that the problem that a lot of people had trouble with. Yeah, sure. Nope, that's not on there. Not yet, right. So if you find the point where I say new topic or something, uh, particle 2D kinetics, it's everything before that. So yeah, no forces, no mass, no Newton's second law. Okay, so exam 2, number 3 was the one, no, not number 3, number 2 was the one that a lot of people had trouble with. And that one says a car is moving 50 miles per hour and hits the brakes. Somebody wrote on their test that they read that as a car is moving 50 miles an hour and hits a bike. And it actually would work that way too, but that's sort of a somber way to write a problem. And stops in 0.1 minutes. How far does the car travel in that time? And we want to express the answer in millimeters. So first of all, you have to convert 50 miles an hour. I'm going to put it all in meters and seconds. So 50 miles per hour is, I think I remember, 22.35 meters per second. And 0.1 minutes is, that's a tenth of a minute. So a tenth of 60 seconds is 6 seconds. And now we can think about choosing a time equals 0 instant, a time final instant. This is a one-dimensional kinematics problem, so a 0 position and a positive direction. Time equals 0 has to be when the car hits the brakes. Time final has to be when it comes to rest. The 0 position, so these two are arbitrary, but I'm going to choose the 0 position to be the car's location at time equals 0. And the positive direction, I'm going to choose the direction of motion. Okay, so time final we know is 6 seconds. The acceleration we don't know. It's not asking for it though. The initial position is 0. The final position is what we're trying to find. The initial velocity, we know the speed at time equals 0 is 22.35. And our positive direction is the direction of motion, so this is positive. The final velocity, at time final, it comes to rest, so we know v final 0. And that's everything. So first we want to look for an equation that has pf in it and everything else in it is known. And there isn't one that works. So the next step is you need to find an intermediate variable. And for one-dimensional stuff, I said the best candidates for intermediate variables are time final and acceleration. In this one, we already know time final, so we want to try acceleration. So we'll put this aside for now and calculate the acceleration. And for that one, I think we should be able to use v final is equal to v initial plus a times time final. So 0 is equal to 22.35 plus 6TF, nope, 6A. And then we can calculate A, and it's equal to, it's definitely going to be negative. Negative. Negative 3 point something. Can someone calculate that? So what is it? 3.725 meters per second squared. And it makes sense that that acceleration has to be negative because the velocity is positive and it's slowing down, it's stopping. So the acceleration has to be the opposite sign of the velocity. And now we know this, and now we can try to find PF. So I guess the equation that we want to use here is PF is equal to PI plus VITF plus 1/2 A TF squared. So PF is equal to 0 plus 22.35 times 6 plus 1/2 times negative 3.725 times 6 squared. And I think that you get 67 point something, 67.05 maybe. I saw these numbers a lot of times. And okay, so that's the answer in meters. And then you have to give it in millimeters. So one thing you can, so there's 1,000 millimeters in every meter. So if you would just want to try to do it in your head, you can just multiply this by 1,000 and that gives it to you in millimeters. Or you can think 1 millimeter is equal to 1 times 10 to the minus third meters. And so 67.05 meters multiply that by 1 millimeter over 1 times 10 to the minus third meters. And the meters cancel. And you get 6.705 times 10 to the fourth millimeters. Any questions about that? So the most common thing people did was calculate the speed, that initial speed, and then just multiply that speed times 6. But remember that would give you the right answer if the speed was held constant over that time, but the speed isn't constant. It's going from 22.35 meters per second at the start to 0 at the end. And so there has to be some acceleration. And so you need to use the constant acceleration equations. Are there any other questions? Yes. Well, no, it's just 0.1 minutes is 6 seconds, not 10 seconds. So you just, I think usually if someone does that and it's obvious to me, like hopefully I didn't take any points off for that. If I did, I'll change it. That's the kind of stuff that's easy to do in a test. Someone also said 270 plus 35 degrees is 295. Whoever that is, I didn't take any points off for that either, so you're welcome. Any other questions on the test? Any other problems you want to see me do or anything like that? Yes. Oh, yeah. For number 4, for A, it's 125 degrees, and for B, it's 305. Or some people use this as negative 55. That works just the same. And if you look it over and you feel like I missed something you wrote or took off too many points for this or that or whatever, I'd be happy to look at it. So come talk to me about it soon. Any other questions on the test? So last time, we were doing Newton's second law. So we're doing kinetics of particles in 2D. And I said that forces can be broken up into 2 types. The first one is the weight force, the force applied by gravity. And then besides that, all you're dealing with are contact forces. And that makes it, if you think of it that way, it makes it a lot easier to know when you've dealt with all the forces in a problem. You deal with the weight force, and then you think about going around the boundary, and there's some kind of force every place that the surroundings are touching the boundary. And then once you've done that, you're done. But contact forces are broken up into a few different types. The first one is pushing contact along a flat surface. The second one is pulling. And the third one is friction. I guess that's all. And so far, we've only talked about pushing contact. And what do we know about the direction of a force when there's pushing contact? We know that it's the force is perpendicular to the surface and toward the chosen body. And we were working on an example where we had two carts in contact with each other. Can someone remind me what it looked like? I think I did this differently in the day class. But we had one over here and one over here, and they were both on rollers. And what were the masses of the two? Okay. And then what was the force from the right? Okay. And um, the first thing we did was we isolated both of those two as a single system and calculated the acceleration. So that's done. And what did we get for the acceleration? I guess it would be -1, 0. And then second, did we isolate the 10 kilogram cart? So our chosen object was the 10 kilogram cart. And we wanted to calculate the force on the 10 by the 20. And for that, we got that, so the magnitude of that force, I think, was 10 newtons. And know that it's a pushing contact, so it has to be perpendicular to the surface of contact and toward the chosen body, away from the contacting body, so it has to be in the negative x direction. And so that is -10 for the x component and 0 for the y component. And both of these we can write in components like this, or we can write it as a arrow pointing to the direction and then a magnitude. So these two ways of writing that acceleration vector are equivalent. And this way of writing the force is equivalent to this. Well, we went through sort of the long process, like drew the free body diagram, came up with Newton's second law, and that. So I guess that would be the answer for where the negative came in. But you can also see, if you just think of, well, the force that we're talking about is 20 kilogram cart pushing on the 10 kilogram. So pushing contact is always toward the chosen body, away from the surroundings where the surroundings are touching it. So toward the 10, away from the 20 is in the negative x direction. And so it has to be a negative x component. And I think it's worth pointing out probably a bunch of times that with these kind of problems, there are usually multiple ways to think about, like, to figure out what direction things should be going. One is you can do it all just mathematically follow all the rules, and you come up with, mathematically, you just come up with the signs of the components, But then you can also think through it intuitively like this. Okay, it's pushing, it has to be going that way. That's in the negative x direction. And it's a good habit to get into to go through the mathematical calculation and then make sure that it makes sense with the sort of intuitive analysis that you can do. You know, it's a good way to avoid mistakes or find the mistakes that you make in the math. And then the last thing that we want to do, we haven't done this one yet, is to isolate the 20 kilogram cart and calculate the force on the 20 by the 10. So that's what we're going to do now. And what do we expect that answer to be? We don't, like, officially, we don't know this yet. We haven't talked about this yet, but I did mention before. And I think it probably makes some sense to a lot of people in here. What do you expect that force vector to be? What? Yeah, that's right. It's going to still have a magnitude of 10 newtons, but it's going to be in the opposite direction. And so the components would be positive 10, 0. Okay, so for part C, we'll start with a free body diagram of the 20. And remember, you have to draw free body diagrams anytime you use Newton's second law. So there's the outline. Then there's a downward force from the center of the object. The magnitude of that weight force is the mass times 9.81. So 20 times 9.81 is 196.2. And now go around the boundary of the object and look for contact with the surroundings. At the wheels, there's contact. And even though that's 2 or 4 wheels, if you think three-dimensionally, I'm going to lump that all into one force that I'm going to call N20. N is for the normal force. And then there's only one other place where the surroundings make contact with the boundary, and that's where I'm pointing the wrong spot. So there are 2 other things going on. Over here at the boundary, there's a 30 Newton force pushing to the left. Right. And then on the left side is the 10 kilogram cart, and it's pushing on the boundary from this side. So that force is perpendicular to the surface of contact, so it's going to be horizontal, toward the chosen body, away from the contacting body, so it has to be to the right. And we don't know the magnitude of that force, so you just have to give it a variable name. And the one that I usually use is a capital R for reaction force. And then write this into Newton's second law. If you do the free body diagram right, every force that you draw on the free body diagram will be represented by a vector in Newton's second law, on the left side of Newton's second law. So the free body diagram just totally, completely gives you everything you need for the left side of Newton's second law. So the force R, that's in the positive x direction, if we use a coordinate system like this. So that's R0. The weight force is in the negative y direction. So that's 0, negative 196.2. The force from the floor is in the positive y direction. So that's 0, N20. And then the last force is that 30 Newton force That's in the negative x direction. So that's negative 30, 0. And all these are equal to the mass of our chosen object, 20, times the acceleration vector, which we know. That was part A. We calculated the acceleration of both of these objects. So this is negative 1, 0. And so what we're trying to calculate is, notice that this vector here is the force on the 20 by the 10. It's just not complete yet because we don't know what that value r is. So when we calculate r, we can plug it back into this vector, and then we have the full vector. Yes. Sure. This one's the weight. This one's the force on the 20 by the ground. And this is the, I don't know, force on the right side. And then this, without that 20 included in there, is the acceleration vector. Yes. Yep. What were you going to ask? Why it's negative? Or what it is? Okay. Yeah, that was just given in the problem. So we don't, the thing is, we don't know what that is. It's, you can think of that as like someone else has already done enough of calculating to just give us that as a that could be like another cart pushing on it, or could be some kind of magnetic thing going on. We don't know. We just know that whatever it is applying that much of a force. Okay, I have to talk to you for a second. Okay. Well, I can't do anything about that now. So we have two equations here. The x equation says r plus 0 plus 0 minus 30 is equal to negative 20. And so r is equal to 10. That's newtons. And then the y equation says 0 minus 196.2 plus n20 plus 0 is equal to 0. So we could use the y equation to calculate n20 if we wanted, but the problem doesn't ask for it, so there's no reason to. But what we do want is, the thing we wanted all along was to calculate this r so we could fill in what's missing from this force vector on the 20 by the 10. Okay, so we're going to use the x equation to find that r. Nope. No, we just totally did this algebraic equation. We just took all of the x components, got an equation that said r minus 30 is equal to negative 20, and then we just solved algebra and it came out as 10. Okay. So yeah, the 10 kilograms, that's just sort of a coincidence. We did it all through Newton's second law and just solved for the variable. And so if R is equal to 10, and this in the red dotted line is the force on 20 by 10, take that 10 for R, plug it in, and that gives us the force on the 20 by the 10. And it's equal to 10, 0 in newtons. Or another way to that is, since it's in the positive x direction, it's a vector in the positive x direction with a magnitude of 10 newtons. And so, just like I said what's going to happen, the force on the 20 by the 10 and the force on the 10 by the 20 have the same magnitude and are opposite directions. Okay, and it turns out that that is always the case, and the fact that it's always the case is called Newton's third law, and it's going to be a big thing in this class. So with these carts, let me say one more thing about Newton's third law. It maybe isn't too surprising, the fact that those forces are the same, but think about like I do this, and I'm like way stronger than this paper. The paper just buckles out of the way. I have no problem punching it down. So what about that case? Like when my hand is in contact with this paper, Newton's third law says that the force my hand applies to the paper is the same as the force the paper applies to my hand. And that's the thing that I think a lot of people find sort of intuitively unappealing, but it's the truth. That's how it is. And you can measure it, and you can't really argue with it. But so try to get your brain ready for that, because that's what we'll be talking about. Yes. Yeah. Yes, you're right. That's exactly right. And actually, that's an example that I use. Um, that I use a lot. I'll use it because I still think it's funny. But yeah, it's fun. Yeah, that's exactly right. Like, yeah, uh, if you well, yeah. So boxing. I mean, if you gently tap someone with your hand, uh, no problem. If you punch someone hard with your hand, you break your knuckles and you go to jail. Um, okay, so get ready for that. That's coming. Uh, any other questions about this problem? Yes. Uh-huh. Yeah. Yeah. Right. Exactly. Yep. Uh, yeah. So right, and it's exactly right, and the forces are the same. It can be confusing in some cases, but that's how it is. So get used to it. Yep. Yeah. Yes. That's a great uh, that's a perfect like sort of connecting point to this. Okay, so think about the two football players, and I think most people would say uh, when they collide. So I said when they collide, we know that the big football player is going to basically keep rolling right along, and the little one is going to go flying backwards. It's going to have a lot of acceleration. That's not because the little football player has a bigger force applied to him. So think about if, say, the force is 1,000 newtons. I'm not sure like if that's realistic or not, but say it's 1,000 newtons. Okay. Um, So the big football player has a force of 1,000 newtons. He's coming this way, pushing this way on him. And the little football player coming this way has a force of 1,000 newtons going that way. Okay. Now the issue isn't that they have different forces. Those forces are both 1,000 newtons. The change in acceleration comes from the fact that mass is a resistance to acceleration. And if you apply 1,000 Newton force to a gigantic thing, it doesn't accelerate very much. If you apply 1,000 Newton force to a smaller thing, it accelerates more. Yeah, well, in that case they can't because of Newton's third law. So yeah, so the forces just are the same. That's just how it is. And how could, like, one way you could measure it, like put uh, so hold up a bathroom scale, you know, facing out, and smash into something. Okay, measure the bathroom scale measures the force. You'd have to do it kind of slowly because they're not very good at quick. But okay, so run into something and it measures the force. Now I don't know how the guts of a digital bathroom scale work, but I mean, it has to be measuring the force something applies to something else. So now flip it around. So now it's measuring the opposite relationship and crash into the thing again, and the force it measures is exactly the same. Any other questions about this problem? Um, okay, let's do one more example. So let's say that there's an elevator and there's a 1 kilogram box on the floor of the elevator and a 2 kilogram box sitting on top of it. And let's say that the elevator is accelerating down at 3 meters per second squared. And we want to know what's the force applied to the top box by the bottom box. Okay, so in the last example, we had the two carts, and we started the problem by isolating both of them together so we could calculate the acceleration of them. And so you might think that that's the first step here too, but in this case, we're given the acceleration. Okay, those two boxes are going to be moving exactly the same as the elevator. So in this case, we can go right to isolating the 2 kilogram box. So I'm going to do a free body diagram of the 2 kilogram box. So there's the outline. And there's a weight force going down of 2 times 9.81, so 19.62. And now go around the boundary and look for contact. The only contact is the bottom box pushing up on the top box. So the force is going to be this direction toward the chosen body. And we don't know what that magnitude is. You could call it N or call it R. Uh, it's just a variable. You could call it anything, but those are the ones I usually use. So we're isolating the 2 kilogram box, and so the weight is the mass of the chosen object times 9.81. So 2 times 9.81 is 19.62. And now we've dealt with the weight, and we've dealt with any place where the surroundings are touching the boundary. So that means we've dealt with all the forces. So now we can go to Newton's second law. The force R is in the positive y direction if we use this coordinate system. So that's 0R. And the weight force is in the negative y direction, so that's 0, negative 19.62. And those are equal to the mass of the chosen object, so 2, times the acceleration, which in this case we're given in the problem. The 2 kilogram box is accelerating like the elevator and like the 1 kilogram box with 3 meters per second squared in the negative y direction. So this is times 0, negative 3. So the x equation says 0 plus 0 is equal to 0. That's reassuring. Actually, that was supposed to be a joke. Okay, it wasn't funny. But if you ever have an equation um, that tells you that like 0 is equal to something not equal to 0, you did something wrong and you need to go back and, it's probably going to affect your answer, So that's the kind of thing that if you ever see something like it shouldn't be that way, that's telling you that you made a mistake somewhere that's going to affect your answer. Then the y equation says r minus 19.62 is equal to 2 times negative 3, so negative 6. And so R is equal to positive 13.62 newtons. And now this is the force on the top box by the bottom box. And so if you just substitute that value for R into that vector, the force on the top by the bottom is equal to 0, 13.62 newtons. Or what direction does the arrow go? So what? Yep, it goes in the positive y direction, and it has a magnitude of 13.62 newtons. And if we wanted to calculate the force on the bottom box by the top box, what would the force be? Yep, it would just be 13.62 newtons down because of Newton's third law. Yes. Oh, you didn't? No. Okay. Any questions about that? Um, okay, so the next thing we're going to talk about is pulling forces. And how do you differentiate between a pulling force and a pushing force? So A pulling force is one where you could imagine separating the objects a little bit. Did I say this last time? And putting and replacing that contact with a little bit of a cable or a string or something. Okay. And if that string doesn't squish, then if the string stays tight and you can still apply the force with that string, then it's a pulling force that you're applying. So we're going to think of pulling forces as if there are cables there, even if there's not. So, um, so in parentheses, this is, we're going to always think of these as acting through cables or strings or whatever. And we're always going to think of replacing the contact with a cable. Once you do that, the pulling force is always parallel to the cable and away from the chosen object. So pushing forces are always toward the chosen object. Pulling forces are always away from the chosen object. Um, okay, so let's say that there's a cart on the ground and this guy's pulling on this cable, this string, um, and let's say that this man, okay, I have to give this a mass. Let's say this is 50 kilograms. And this man pulls on the rope with a force of 20 newtons. What's the acceleration of the cart? Um, well, he probably shouldn't be working that hard because that's something like 4.5 pounds of force that he's applying. But we want to isolate the cart. So draw a free body diagram of the cart. And now we'll go through the forces. There's a weight force acting down. That's 50 times 9.81. So that's 490.5 newtons. And then there's a pushing force up from the ground. I'll call that N. And then there's the pulling force. Um, and we know the magnitude of that force is 20 newtons. The direction of that force is parallel to the cable that he's pulling on, away from the chosen body. So it's going this way. And actually, I think one nice way to darn it. Um, One nice way to keep track of the direction that the force that pulling force applies to the object is to imagine including in so the body that you isolate, imagine that we're isolating the cart and a little like 1 millimeter of that rope. Okay, so then it would look something like this. I don't know. Okay, well, so say then we're including like a little blip of like a little stump of the rope, you know, is included in the object that we're isolating. So if you draw that little stump of rope, the pulling force always just points right out of the stump. Okay. It's not too hard to, that doesn't help too much in a problem like this. But when they get more complicated with pulleys and all this stuff, sometimes that's a useful uh, thing to just sort of center yourself on where it goes. Okay, and the magnitude of this force is 20. So now Newton's second law says 0n, because that's the positive y direction, plus 0, negative 490.5. The 20 is in the positive x direction, so this is 20, 0, is equal to the mass of the cart, 50, times the acceleration. And I, I said last time that if you have rolling and sliding problems, there's not going to be any acceleration perpendicular to the surface. So I'm just going to call this A0. The acceleration is all going to be in the x direction. And you don't have to worry about the signs. The signs will work out on its own. You just have to get the dimension right. And then the x equation says 0 plus 20 is equal to 50a. So a is equal to 0.4 meters per second squared. This is the acceleration vector. And so plug this a into the acceleration vector, and you get that the acceleration vector is equal to 0.40. Or since that's the positive x direction, this way with a magnitude of 0.4 meters per second squared. Any questions about that? Okay.